Sorry? Ah, yes. Thank you, Aparna. And thanks for coming. So I don't know if the mic works. Sorry? Yep. Okay. Okay. So what I want to talk about today is a question that we've been working on with Tony and Gabriel. Lelièvre and Stoltz. So it's a question related to metastability. First, I'll do a bit of motivation. Of course, the clicker doesn't work anymore. Okay. Okay. So first, I'll motivate a bit about why we were interested in this question by reminding everyone of the timescale problem in MD. So typically, if you want to increase the number of atoms you want to simulate for a given time, you can take advantage of parallel computers and just basically have bigger computers to simulate bigger systems. But when you want to access larger timescales, then you're out of luck because you need basically faster clocks on your computer just to increase the frequency of your time step. And that's a big problem because what we want to access in terms of the phenomena is in this timescale range that we can presently access. So in the ideal case where the scaling is linear on both in time and in space, is this region here? So in space, we can basically push the boundary proportionally to the amount of compute that you can add. But here we don't know how to do this with naive methods. So what I want to talk about is we're working on this problem. We're pushing the boundary of this space of accessible simulations towards this region. Okay. So this the class of methods we're interested in is something that comes from Arthur Rotter, accelerated dynamics method. So in the late 90s, Arthur Rotter introduced the three big classes of methods to accelerate the dynamics. And the idea each time is to exploit metastability to speed up transitions. Okay. So metastability is what happens when the dynamics is stuck in the local state of configuration space, omega. Okay. And transitions out of the space or out of the state are a very rare event, which ideally we want to sample quicker. So mainly I'm going to talk about this third algorithm, parallel replica algorithm. And the idea is somewhat seems naive at first. It's really the core idea is that when you're stuck in a local equilibrium, you can launch many independent replicas and just follow the first replica to escape the state. Okay. And that should give you some consistent estimate of where the system will go after this transition. Okay. We need to be a bit more formal about this, but basically it's that. So I also mentioned briefly that there's other techniques like temperature accelerated dynamics. You speed up transitions by heating the system, okay, and then apply some correction. And the hyperdynamics where you bias the potential to reduce the energy barrier. But this is a very general approach. Really. The only thing it assumes for the dynamics is that it's Markovian, and that there is some notion of local equilibrium in this state omega. Okay. So how do you formalize this mathematically? It's with the idea of the quasi-stationary distribution. Okay. So here we have this dynamics xt, okay, which lives in RD configuration space. What is a QSD? It's a probability distribution on omega, the metastable state, which verifies the following condition. So if you start the dynamics distributed according to new so the QSD. If you look at the probability that xt is in some state, conditionally on x on the trajectory we have not left the state. Okay? This is what it means. So xs is in omega for every s into t. Then you're still distributed according to the quasi-stationary distribution. Okay. And so another thing, another way which is perhaps more natural to think about is that the quasi-stationary distribution is the law of the process conditioned on being stuck in the metastable states for an infinitely long time. Okay, so you completely forget how you entered the domain. You just you're stuck in this local equilibrium. Okay. A is any arbitrary state subset of omega. Okay. Basically, it tells you that the law of xt starting from nu, conditioning on not escaping, is still nu.
X state is the substate.
Sorry?
The XS.
XS is just the dynamics.
States.
It's the dynamics. It's
So?
it's the state of the dynamics at the SSE.
No, I'm talking about XS.
XS is the dynamics at time S.
Okay.
Before T. So if you denote tau the exit time from omega, the key property that we really exploit in this parallel replica algorithm is that it's exponentially distributed. So exponential random variable with some rates and all that. And the exit point, x tau, so x tau is really the point at which you exit. It's independent of the time. Okay. So why is this property useful? Well, it means that if you sample independent replicas at initial time according to the QSD, okay, and you just look at the first replica to escape, then the exit time of the first replica to escape is still exponential with rates lambda over n. Okay? So you can get an estimate of tau just by multiplying by the number of replicas n. Okay? And then the exit point is a consistent estimate of the exit point for the original dynamics.
How do you know without predicting whether the state is escaped or not?
For now, we just assume that you know if it's a mathematical definition, right? So you just assume you have a convenient way to define the state. Okay? It's given to you. The state is given to you. And, exactly the question we will ask is how to choose the state to get good probabilities. So we're going to exploit this property to speed up the computation. So how does this look in practice? So you have this algorithm. Okay. So let's say you have some definition of the metastable state, and you detect that your dynamics has entered the state. Okay. So once you enter the state, then you're going to spawn independent replicas. You're going to dephase them in the state to make them independent. So you're going to decorrelate them to make them independent, and then wait somehow, I'm not going to tell you how exactly, until the replicas have reached the QSD. Okay. So if they don't escape, so for instance, you can do just rejection sampling, just by keeping the replicas that haven't escaped. You know that after a long time, some defect in time, then all those replicas are going to be distributed according to this QSD, this local equilibrium. Okay. And once you have a bunch of replicas distributed according to the QSD, then you can do the sampling of the exit event, and you speed up the exit time, expected exit time, by a factor which is given by the number of replicas that you need. Yeah. That's it. So the game is in this parallel step. where you sample in parallel the exit event.
Why do you get replicas? You can simply do an MD calculation and then sample. Because the same well, right?
Sorry?
They're in the same well, so you could just do an MD calculation and generate.
So really the point is we want the dynamics. You want to know the
So why
property.
do you start from multiple replicas? Basically, you want the sampling for your well, right?
No. That's really not the point. We want to get the statistics of the transition. Speed up the transition to the next one. And so yeah, you can do that in parallel. So what you could do is have a bunch of replicas from the start. You just do MD independent MD runs.
So instead of doing replicas, if you do just one MD calculation for sufficiently long duration, would it not sufficient to generate that QSD?
But if it doesn't, yeah, not sure. The problem is not generating the QSD. It's not problem. The problem is finding the statistics of the next function and following the dynamics across a long time.
That's right. You can always do it with one long and deep predictive.
Yeah.
You can only visualize so many cores, right? It's like one directory, you can only have like 10 cores or something. Now with this approach, you can use hundreds or thousands of CPU cores, all running in parallel, all finding.
Basically, the sampling is space.
So it's the parallelization is happening in time. That's the unique part about it.
Exactly. We're parallelizing time. Exploiting this property of the QSD, which has this exponential distribution of the exit time. So yeah, what you gain is this parallel sampling in time of the exit event.
Someone has a question?
Hi, Noé.
Hi.
Hi, can you hear me?
Yeah. Who is this?
So, in your QSD part, so is there any biased potential there, or just a parallel replica?
So this is just a mathematical definition, right?
Okay.
So in practice,
so there is no biased potential, right?
bias potential.
To make the local minimum jump out of the basin. So, is there any biased potential there?
No, not at this stage. At the moment, it's just running in parallel. There's no bias in parallel.
Oh,
Well,
okay. Just
so
okay.
there is a small bias going. So in the limit of infinite decorrelation time, then that's correct. Yeah, there is no bias.
Thanks.
But in practice, you choose a finite decorrelation time, and then you introduce some bias because you're not exactly distributed to the QSD. Yeah. If you're stuck for some finite time, you're not exactly at the QSD, but actually you can show that you're exponentially close to the QSD. So I'm going to
Okay.
Okay.
Thanks.
Yeah. Okay. So what I was saying is that the overhead of this method is really the preparation of independent replicas according to the QSD. Okay. And that costs you a lot because you're also running MD in parallel on many cores. If this stage of the algorithm is on. Okay. So what you want, if this is the typical exit time from the state, to be much longer than the typical decorrelation and phasing time. That's what I write here. Okay. It turns out that we can get a mathematical handle on these quantities, okay, which depend on omega, the state, the definition of the state. And then we can sort of optimize the state to make this as true as possible. Okay. So now we get into the math part. So this is the mathematical link that was discovered by Gabriel, Lelièvre, Materials and then Perez, which gives a very nice characterization of the QSD in the case where your dynamics is given by this overdamped Langevin dynamics, okay, which samples the canonical configuration also. So here you have this gradient of the potential, and this Brownian term, which I will soon about this. So in this case, the causation distribution in omega, you can simply write it in terms of a certain function, Q1, which is given as a solution to an eigenproblem. Okay, in omega. So here you have a differential operator. Ah, I forgot. Here there should be delta. Delta minus 1 delta. So the Laplacian. So this is the generator of the dynamics. And you say you look at the first eigenvalue of this generator with absorbing boundary conditions. So U1 is something that cancels on the boundary of the domain, and which has this which satisfies this eigenrelation. What you can show on top of that is that the exit time, so the average exit time from the QSD is given by the inverse of this eigenvalue. Okay, so lambda 1 is an exit rate from omega if you start from this quadratic spatial distribution. So here I had this lambda parameter. And now we know what this lambda is. It's the eigenvalue. Okay. Is that clear? It's a bit scary, but
So what guarantees that you become zero on the boundary?
that's by definition. So
Well, that's how you're going to define.
that's the definition. It's a theorem that the QSD is given by this. Is given in terms of the solution to this eigenproblem.
We don't want the nodes to be in the same.
Yeah, that kind is good. Just
Yes, so it makes sense that U1 is 0 on the boundary. So remember
there could be some weird discontinuity, that's okay.
sorry?
There could be some weird discontinuity at the edges of omega, that should be okay.
So the discontinuity of what? Of the,
So the U becomes zero
What?
in the boundary of what you're.
yeah, but well, it's getting into some more technical points, but it's regularized by the fact that this is really elliptic boundary, elliptic different P. Okay, so you have so you have delta Q1, which I forgot, I'm sorry. But so that makes the solution regular. So you have guarantees that actually there's no real discontinuity. Okay, but the main point I want to drive home is that this lambda 1, the second value, is the inverse of the exit time. It's the thing you want big to make the algorithm very efficient. You want to be stuck as long as possible. The second theorem that makes the mathematical link, and that answers your question about the bias, is the following. So if you condition on being stuck in the state for a certain time t, then the difference of the law of the exit event you're going to sample, starting from this condition law, with respect to the ideal thing you want to sample, is exponentially small. Okay. Basically, if you stay stuck in the state, you converge to the QSD exponentially fast, and the rate is given by the spectral gap, lambda 2 minus lambda 1, of this very same operator in omega, with some boundary condition, 0 boundary condition in omega. The second eigenvalue. Okay. And this rate is the thing that tells you how fast you converge to the QSD. Is the thing you want to be a really big. Right. You want to converge fast to the QSD, and then you want to exit slowly from the QSD. So it gives you some kind of spectral criterion on the domain for the efficiency of the algorithm. What we want is to maximize the spectral gap. Okay, and also maximize the inverse of the exit time. So in a sense, you want to maximize this ratio. So that's all. In a phrase, make the exit time large compared to the decoration time. Okay, and more conceptually, if you want to increase the separation of timescales. You have this timescale of decorrelation and this timescale of transition. You want to make the decorrelation timescale as small as possible in front of the transition timescale. So what people do in practice, so they use an implicit definition for the state, and they just do typically choose omega to be the basin of attraction of the domain of the dynamics for some minimum. You take a point, you relax with a steeper descent to the minima, and you say, okay, my state is this minima. It's a state attached to this minima. Okay, as we know that can't be the best choice at positive temperature, because what happens is you're gonna have reprocess. Okay? So you detect an escape from the state, which actually not an escape at all, because right after you come back to the state, and actually you stay in the state for quite a while. But if you do that, you sacrifice an opportunity to use pareil for a bigger domain, and just have this parallel. Now you have to regenerate samples according to electricity, and that's very inefficient. Okay, is that clear? Is the general thing idea we want to do? We want to choose omega to make this as big as possible. Is everyone by that?
So maybe also a graphical way to think about it. We have like a very deep potential, and then it's easy to get stuck, and you have a very slow exit time. But if it's very narrow state, it's much harder to identify and use to accelerate, right?
Yeah. But for now, we don't make any presumptions. We just have this spectral continuum, which we want to maximize.
But for me, at least, sometimes it helps on the applied side to think about like an example.
Okay. So what's the first thing we can do? Okay. So we have this quantity, we have this parameter, which is the domain, omega, which is optimized with respect to the domain. So that's a question of shape optimization of eigenvalues. Okay. And so what we can show, we're going to see, is the following. So if you take a certain map, which takes theta. Okay. Theta is going to be a vector field. It's going to be a perturbation of the shape. And so here you transfer the shape by this perturbation field. Yeah, omega, you just twist it a bit with a theta. Okay. You transport the shape according to theta. You can show that this map, when theta is small, so around 0, this is differentiable with respect to theta. And you get an explicit expression of the derivative of the eigenvalue, which is this formula. So unpacking this a little, what is this? It's a boundary integral, which has a term which depends on the corresponding eigenfunction. And this then has this the normal component of the perturbation direction. So that makes sense, right? So if you take a perturbation which is tangent to the boundary, what you're doing is just twisting the boundary on itself. Okay? So it shouldn't matter, it doesn't affect the shape at all. And similarly, what you do inside the boundary has absolutely no bearing on the general shape of the boundary. So as a sanity check, this is not necessary. Okay, now once you know how to differentiate eigenvalues, then you can do gradient descent on the shape. So basically, you choose the perturbation field, which gets you in the direction of lowering this ratio, of maximizing this ratio. Sorry. and you just step and you iterate, and you can optimize iteratively using first order optimization methods. Okay, so what does it look like? This is the converged results for the shifting potential wave. So what I plot here is a heat map of the potential. Okay. So you have this. This is the map, okay. And we initialize the algorithm like a real small ball around the minimum. Okay. And then you do this shape optimization procedure. And what you find is beta equals 3, so if you're in a hot system, you want to start really a lot. But if you decrease the temperature, you sort of concentrate on the wet. Beta equals 6. And if you continue, you come closer and closer to the summit. So it's a qualitative result. Just you observe numerically with this simple 2D system, all 2D systems, that you have this concentration in the low temperature of the optimum domain towards this local energy. Okay. And that makes sense if you think about it, just intuitively. That at a low temperature, once you pass the saddle, there's a very slight chance of recrossing into the web. You're basically guaranteed to leak out to the web. So you don't need to go very far outside of the saddle to guarantee that the exit is real exit. Okay. So,
Can you explain the color code again?
it's the heat map of the potential.
So the yellow is
Yellow is a low. The minimum is here. The saddle is here.
okay.
Okay. You have the saddle points. You have the minimum. And you
Okay, so there's, because I just saw that the ISO value for me it's like just the 2 or something, but I didn't see the minus and stuff.
there's a minus. Yeah, and this is a vertical system. If you think that the beta equals 9 and the Dari hat is 2. Okay, so I don't know in non-dimensional units at least. You have the exit time is something we know from Arrhenius law that it should be exponential and minus beta times the Dari hat. So that's exponential 18. It's very cool. And still you have the decent spilling out of this. Okay, but of course you can do this for real systems. This can be real person. So even for a 2-dimensional system, you have to solve an eigenvalue PDE at every time step. If you have 100 atoms, you have an eigenvalue problem in 300 dimensions. It's just not possible. So what we would like to do, so the second strategy, is to parameterize the family with just a handful of parameters, so low dimensional parameterization of the domains. And we want to find the best alpha in terms of the asymptotic criteria. Okay. So take beta goes to infinity, so the low temperature limit. If we find asymptotics for these quantities, then we find the asymptotics for the ratio, of course. And we want to optimize this asymptotics. Okay. This is a strategy like so it won't be a finite temperature, we won't get optimal domains. We get sometimes things that behave optimally in the low temperature limit.
So you start at the low temperature and then you ramp the temperature up, or?
No, so we do just mathematical analysis this way.
But that means you already know the whole potential landscape.
No. For the sake of mathematical analysis, we know everything. Okay. And so it becomes a question of practice. How do you use this analysis to derive a practical algorithms? That's a question that's interesting and not quite easy. But mathematically, we have a question which is just a find set asymptotics of eigenvalues when the boundary moves, the domain moves with the time. So I'm gonna pass on this, but for those who are interested, this is a sort of mini review of previous work in this field, spectral asymptotics and low temperature limit, and applications to metastability. So it's really a rich domain. So if you're interested, we can chat about this. Okay, so what we do exactly in our analysis is we look at domains which look like this around saddle points. Okay, so what's on this figure? Here you have some saddle point Zi, and this blue line, this blue vector here is the eigenvector, negative eigenvector of the Hessian of the potential. So it's the unstable direction. Yeah, the saddle point, you have the z-1 stable direction and 1 unstable direction. This is the direction of the unstable direction. And we push the boundary to a certain distance along this this unstable direction. Okay? And you allow some leeway. Okay, so the boundary is not necessarily exactly that, but it's close to being a hyperplane, which is pushed out or inward actually in this unstable direction.
Can you make a statement whether you push it in more like to the minimum or not to the?
So actually we push it just a little bit. And so what we write here is that so you have this parameter which is alpha I, which is going to modulate the distance of the boundary to the south point. But it's really small. Okay, for the distance is going to be really small. So you have you multiply this square root of beta. Okay, so it's something. But the distance is something which is order 1 over square root of beta.
But you measure it in comparison to the saddle point, so it
Yep. Yeah. If you're outside, imagine the saddle point is here, where the pointer is, then you will have a negative alpha. Okay. And so our parameters is going to be the asymptotic behavior of this distance.
This eigenvector same as the eigenvector of pronouns.
Sorry?
You do pronoun calculations.
Mm-hmm.
You get the imaginary.
So the difference here is, remember you have asymptotic, sorry, you have boundary conditions.
But my question is, the eigenvector that you have drawn, is it same in your case as that would?
It's the imaginary frequency of the phenomenon.
They're the same.
Yep. Oh, no, sorry, it's an eigendirection. The eigenvalue would be.
Yeah.
Well, this
Yeah, eigenvector.
the eigenvalue would be the square of the frequency. Okay. And so, somewhat of a, so this is our parameterization, the parameterization we choose for the but it's somewhat natural, okay? Because we know that the minimum energy path at the saddle point is going to be tangent to this vector. Yeah. So what we're saying basically is we're looking at domains which are roughly perpendicular to the minimum energy path around the saddle. Okay. So they're parameterized using a reaction coordinate, which is natural. Okay. So now we have our family of domains, and we're going to look at the asymptotics of our eigenvalues with respect to alpha. Okay, so the first theorem we have is the limit of the any eigenvalue actually. We take any finite eigenvalues, and we show when beta goes to infinity that it converges to some eigenvalue, or the eigenvalue of some operator, which we can compute explicitly. Okay. And which is some kind of harmonic approximation. It's really similar to what you do when you don't have a boundary. But the point is you can exactly compute the eigenvalues of this operator. So you can compute the limit of this function. And just as an example, if you say you have only one minimum and only order one set of points in the domain, then you get this expression for lambda one. Okay, lambda one goes to 0. So when beta goes to infinity, it just tells you that it takes infinitely long time to escape the low temperature limit. It's reasonable. And then you have this expression. So I'm not going to comment too much. But the point is you can compute this using the eigenvalues of the Hessian. And here you have this this new thing, which is related to a certain quantum harmonic oscillator, the ground state of a certain quantum harmonic oscillator, but with an infinite potential barrier. It's a parameter. Okay. So how much time do I have? Are you okay with that? Okay.
Wait 5 minutes.
Okay. So yeah, I'll speed up a bit about the thing. And the point is, we have. Okay, so when you have this, we want to compute the asymptotic of the ratio because lambda 2 is over lambda 1. So this we have the asymptotic, but asymptotic of lambda 1 goes to 0. That's not fine enough. We need finer information. And so this is what we did. So we showed a kind of Eigen-Kramers formula. So this tells you that the eigenvalue is exponentially small in the barrier height. Because this is standard Arrhenius behavior. And then you have this Q-factor, which depends on alpha. Okay, it depends in a very simple way. Actually, it's just you take a CDF of the eigenvalue of the Hessian, the negative eigenvalue of the Hessian. So this really is the fundamental frequency. Right, the square root of the imaginary frequency times alpha. But the point is, we have some asymptotic, and now we can really fulfill our objective, which was to optimize the asymptotic behavior of this ratio. Okay. And here I'm just writing it for the case of a single set point, because it's instructive. So you have this term exponentially high in beta, which doesn't depend on alpha. Okay, it depends if you can move play with the domains as much as you want. You will never beat this exponential factor. That's just a large deviation. So you can't play with this. But what you can play around with is this lambda 2, and the part of the Q-factor in this formula, which depends on alpha. Yep. Okay, and so if you manipulate with this expression, you arrive at this thing. So this is like the prefactor of this thing, which we want to maximize. And it comes out that you want to maximize this function J of kappa and theta. So kappa is just the ratio of the curvatures between the unstable curvature at the south point and the soft curvature at the minimum. And so now you have this objective which doesn't depend on alpha. And it's just a 2D thing. Okay? So you can fully optimize it. And you get a recipe to find the asymptotically optimal boundaries in the limit, in the low temperature limit. So we do exactly that. Okay. So you have this reduced objective. And what I write here is the curvature ratio between the saddle point and the minimum. And here I plot theta, okay, which gives you the distance of the boundary to the saddle point. In red, I plot the optimal theta. Okay. And so once you have this, you have a way to parameterize domains, at least in the case where there's only one saddle point. And what we find also is that the efficiency, it also gives you an estimate of the maximum parallel efficiency you can gain from this, from modifying the boundary. So when you go to kappa equals 1, which is when the saddle is just as short as the minimum, you basically double the parallel efficiency. This is expected because well, basically you're just capturing all the reprocessing. When you're at the saddle, basically you have a 1.5 chance to go back to the minimum, and 1.5 chance to escape. And if you capture all the true escapes, then you double the efficiency. So we don't expect that you can do that. And then the softer the saddle, the lower your maximum efficiency gain, until about 17% saturated. When the saddle becomes twice as soft as the similarly on skip that, and if you have any questions, you have to answer them. I hope at least got the point across of what we're doing.
And what we need to practically
Yep.
understand this.
Okay.
It still requires the knowledge of the whole.
Okay, so there's two ways to look at this. If you want to find the real asymptotics of this thing, then you need to know all the minima, you need to know all the critical points, and so on. So it's pretty hopeless, and you're including the maxima, basically. But I think in practice, what you would do is to just reduce everything to the case of one cell point and optimize the domain locally. So once you find the cell point, then you can parameterize your boundary using this criteria. And that gives you a practical way a sensible way at least, to capture some repressing in a principal way. But what you need is you need to find cell points and you need to compute eigenvalues of the Hessian. And that's it.
We just have a single barrier. Whereas there are also approaches where you have like multiple barriers that are moving closer and closer from the.
Well, yes, we're in single one. We're optimizing around the single image. Yeah, so it's the case where I think the answer is less important than the question somehow, which is how do you optimize the domain to get maximum efficiency for the algorithm.